Okay, um, let's pick up where we left off yesterday on 4.5. So 4.5 is on they call it a summary of curve sketching. Basically, we're going to use all the information that we've got so far, bunch of pre-calculus ideas, bunch of calculus ideas, put all the information together, including sometimes we're going to be using limits to come up with what a graph looks like. And we did one yesterday. We did this one right here. And there's a little acronym. The book has us go through these 6 ideas. So domain, intercepts, symmetry, asymptotes, and intervals of increase and decrease, and then concavity, in order to come up with what this looks like. And sometimes it might seem like a little bit of overkill. And again, the point is not that you've got a powerful tool in your hand that could make this graph for you. We want to understand why the graph makes the shape that it does. And understanding the calculus behind it, the algebra behind it, the limits behind it, and that sort of thing can help us with that. So we did this problem yesterday. I went through, and one thing we didn't do is we didn't find the second derivative. So I went through and did the work for finding the second derivative here. So there's the quotient rule. I factored some things out, and this is what we end up with right here. So I'm going to zoom in on that right there, and let's talk about this for just a second. We have the correct graph, but I want you to think about this being the second derivative here. We'd want to know where the derivative equals 0. So let's take a good look at this. The only part of this that could make this equal to 0 would be the numerator. Does the numerator ever equal 0? Nope. Positive value here. And this would have imaginary zeros to it, so no real zeros to this one right here. So the numerator never equals 0. We'd also want to know where the second derivative doesn't exist. The only places where it doesn't exist would be where the denominator equals 0, which we've already got up here. We know those are points of discontinuity. So we know it's got to have the same concavity on these intervals here. So if I find that it's concave up here, the whole thing is concave up. There aren't going to be any points of inflection on this graph, in other words. Okay? So let's look at this, and let's think about this for just a second. Okay? The numerator is always positive. So the only way that this is going to change sign, or let's say when it's going to be negative, is if the denominator is negative. Because if this is negative, I'd cube that, I'd get a negative. So when is x squared minus 9 negative? Yeah, when it's less than 3 in absolute value. In other words, when you're plugging in a number that's between -3 and +3, that's the only time the denominator would be negative. That's the only time the second derivative would be negative. So if we look up here, isn't that where it's concave down? Right there. Okay, so no surprise there. So we know it's always curved upward here, and always curved downward there. Okay? All right, so I've got about 46 minutes to do 4 problems. Let's see if we can do it, okay? Now, on this first one right here, we've got a bit of an advantage. You do have some problems like this, and I would consider these very fair game, even if you weren't given the derivatives, okay? These are graphs that we're already familiar with. They're relatively simple to work with because they're polynomials and power functions. I've got the derivatives written down here, and so let's run through these ideas. We want to think about the domain. The domain is all real, so we don't have any domain issues with this. We want to find intercepts. So if I find the intercepts for this, the easiest thing to plug in is the y-intercept. If I plug in a 0, I get a 0. Okay, so that's the y-intercept. It also serves as an x-intercept. Then I want to find any x-intercepts. So I'm going to set this equal to 0. So if I set that equal to 0, I probably want to factor that. So I'm going to take out an x squared, and I can take out a 4, and I'm left with an x and a -3. Is that correct? Good there? So I've got an x-intercept of 0, happens to have even multiplicity if you remember that, and I've got an x-intercept of +3. Okay? So I've got an x and a y-intercept at the origin, and then I've got an x-intercept at 3, 0. Okay? So let's see, disaic, D-I-S, what did S stand for? Symmetry. So let's check symmetry. If you plug in a negative x, and then simplify the result. Okay, we want to see if this is basically odd or even. So this is going to be negative 4x to the third, and this is going to be minus 12x squared. So we compare this to the original one. If it's the exact same, it's even. If it's the exact opposite, it's odd. And if it's neither of those, then it's neither. What is this? Nope. Because there's three negatives here. Square that. Good? Okay. So it's definitely not exactly the same, and it's not the exact opposite. So this is neither. So there is no symmetry. Okay? Okay, the next thing we want to check is we want to check asymptotes. Okay, now I realize that we know this looks like the power function, 4x to the third. So we know what the end behavior is. It's going to start down here and it's going to end up here. It can have up to 2 turning points in this. But let's just double check this. Let's check the limit as x goes to infinity on 4x to the third minus 12x squared. What's the most dominant term here? The cube one is. So if we plug in a positive infinity, this is going to tend to positive infinity. Okay, I'm just going to change colors here. If we were approaching negative infinity, the most dominant term here would again be the cube. If you plug a negative in, you're going to cube that. You're going to have 3 negatives. So our limit's going to be negative infinity. Okay? So we know that on this end, so limit-wise, we've just confirmed what we know about an odd power function. It's going to head down this way, and it's going to head up this direction when it's done. Okay? So domain, intercepts, symmetry, asymptotes. Let's check intervals of increase and decrease. So for that, we want to use the first derivative. Okay? So the first derivative, we'd want to know when it equals 0 or when it doesn't exist. It's a polynomial, so it's going to exist everywhere. So let's factor out a 12 and an x, and I'm left with, let's see, an x and a minus 2. Good there? So it equals 0. The first derivative equals 0 at 0 and at 2. Okay, so I'm going to make a sign line here. And on the sign line, remember, we've got values of x, and I'm going to put 0 on the sign line, and I'm going to put 2 on the sign line. And the reason I'm putting it there is the derivative is 0. The first derivative is 0 at each of those locations. Then I'm going to plug in a number on this interval, a number on this interval, and a number on this interval. So if I plug in any negative number you want, okay, that's going to be a positive 12. That's going to be a negative number. And if I plug in a negative number here, that's going to be negative. So the sign of the first derivative is positive on this interval. If I plug in a number between 0 and 2, so if I plug in a number between 0 and 2, let's say we plug in a 1. Can't do anything about the 12. That's going to be positive. Okay. I'm plugging in a positive 1, so that's going to be positive. And 1 minus 2 is negative 1, so that factor is going to be negative. So I've got 1 negative. That means the first derivative is going to be negative on that interval. Pick any number you want past 2. Pick 17 if you want. The 12 is still positive. We're plugging in a huge positive number here, and we're plugging in a number that's bigger than 2 here, so even when I subtract 2, that factor is still positive. So I end up with a positive first derivative there. Any questions about that? We've done this several times, right? Okay. So I'm going to go ahead and erase that work there. The reason we keep track of that information is because the first derivative will tell us how the original function is behaving. So we know the original function is increasing. It's leveled off for just a second. Then it's going to decrease. Then it's going to level off. And then it's going to increase. So we could actually draw kind of a rough sketch of what's going on here. It increases, levels off, decreases, levels off, and then increases. Okay, now, just with a sketch, to the blind eyeball, this looks like this would be concave down and then concave up here. So there's probably a point of inflection. So let's use the second derivative. So I did that work here. I'll bring this down here. I want to know where 24x minus 24 is equal to 0. So I take out a 24, and that's equal to 0, whoops, at x equals 1. So I'm going to put a 1 here, right there. And the reason that's on my sign line now is because the second derivative is 0 right there. And if I plug in a number on this side of 1, let's say I plug in a 0. Okay, so kind of like using the second derivative test. Okay, the first derivative is 0. If I plug in a 0 into this value, into this second derivative right here, do I get a positive or negative? I get positive 24 times negative 1. I get negative. Okay? So if the first derivative is 0 and the second derivative is negative, it's concave down. I've got a max right there. I mean, we can tell that by the increasing and decreasing intervals, but that's good confirmation there. And if I plug in a number on this side of 1, so let's say I plug in a 2. If I plug in a 2, I've got 24, which is positive, times 2 minus 1, which is positive. So I end up with a positive second derivative there. So that means we're concave down here and then concave up here. So that means I do have a point of inflection. And what is that point of inflection? What's the x-coordinate of that point of inflection? 1. So it's 1 comma something. And to find that value, let's plug in here. So if I plug in a 1, I get 4 minus 12, so I get negative 8, right? Okay, so let me highlight some of the things that we want here. I know those 2 points on the graph for sure. Those are x and y intercepts. I know this is a point on the graph. I know it's a point of inflection. I know where it changes from concave down to concave up. Okay, and I know these intervals of increase or decrease. And I also know I've got to have a max right here, and I've got to have a min right here. So at x equals 0 and at x equals 2, I've got to have a min. Or sorry, max here, min here. So let's draw this graph. Let's see, I've got the point 0, 0, and 1, 2, 3, 0. I've got a minimum at 2 comma something. Let's plug in a 2. So if I plug in a 2, I end up with, let's see, this is going to be 32 minus 48, right? 32 minus 48, so that's going to be negative 16. So I've got a point down here at 2 comma negative 16. I've got this point of inflection right here at 1 comma negative 8. And the graph does something like this. It increases and is concave down here. Levels off for just a second, comes down like this. Still concave down. Then it starts to kind of make a turn. Go like this. All right, that doesn't look very good. Looks like that. And if I label these points right here, certainly couldn't ask for any more on a test without the use of a calculator. Those are all the important features on here. Okay, any questions? Sure? Okay.
That's pretty cool because now we can figure out exactly where.
Yep. No, I mean, all the important details are represented there, and we know why it makes the shape that it does. Okay? All right. Good? Okay, let's take a look at the next couple. So I've got 3 more that we want to take a look at. Hopefully we'll be able to finish each one of these completely. Let's take a look at this one right here because this gets a little bit interesting because we've got a function e to the x over x. Probably not something that anybody in here has graphed before. Let's run through here and let's identify the issues. Okay, I want to check the domain. What number can I not plug into this? Can't plug in a 0. Okay, so I know there is no value at x equals 0. We'll figure out what happens there in just a second. I want to check the intercepts. So if I plug in a 0, well, wait a minute, can't do that This means there's no y-intercept. This does not hit the y-axis at all. Okay, let's find the x-intercept. Let's set this equal to 0. So I want to take e to the x over x, and I want to set that equal to 0. The only way that could equal 0 is if e to the x equals 0, and e to the x is always a positive function, so this never equals 0. So there are no intercepts of any kind. This does not hit either axis. It's a big piece of information. Let's check the symmetry. We want to check to see if f of negative x is the same as f of x, or the opposite of f of x. So is e to the negative x over negative x? Well, gosh, all you can write there is e to the negative x, or negative e to the negative x over x. Is that exactly the same? Exact opposite? Nope. Not the exact opposite, because notice we've got this negative in the x. Okay? So no symmetry. Okay? So we've got to figure out what it looks like on both sides of the y-axis and both sides of the origin. Okay? What's up next? Asymptotes. Okay, now, what happens when you have 0 in the denominator normally? What do we normally have on a graph? We normally have a vertical asymptote, right? So we're going to check the asymptotes, and again, we're going to use the ideas that we've talked about in this class. So I'm going to check the limit as x approaches 0 from the positive side. Let's check what happens on the right side if I've got e to the x over x. So let's think about this for just a second. If I could plug in a 0, I would, okay, and I'd end up with something really close to a 1 on the top, a positive 1 on the top. I can't plug in a 0, but I can plug in really small numbers. Okay, if I'm approaching 0 from the right side, these are all positive and approaching 0. So what if I have a positive number on the top, and I'm dividing it by a positive number that gets closer and closer to 0? Positive infinity. Okay? So what that means is, on this side, it's going to go up. Let's check and see what happens over here. So we're going to check the limit as 0 or x approaches 0 from the negative side. That doesn't change the fact that the top is positive and approaching 1, but it does change the bottom. The bottom is now, we're plugging in a negative, and it's still approaching 0. So what's its limit? Negative infinity. Okay? So I know that on this side, I'm heading down. So I know the behavior of the function on either side of this vertical asymptote. Okay? Well, this is also an interesting function because of the end behavior. So let's check and see what happens as I approach positive infinity. And I'll let you think about that for about 5 seconds. Very good. L'Hopital's rule, right? Because I get infinity over infinity, so we'll apply L'Hopital's rule. And when I do that, I get the limit as x approaches infinity. This is going to be e to the x over 1 now. So this is going to be, well, the limit would be infinity because e to the x continues to grow, right? It gets larger and larger and larger. So here's what I know. Let me see this little sketch right here. Okay, this is a piece of garbage, but it's got a whole bunch of information on it. I know that it approaches this vertical asymptote and goes up, and I know that on this side it goes up like that. Let's check and see what happens as x goes to negative infinity. So again, I get e to the x over x. Well, let's see. As I plug in a larger and larger negative number on the top, what does the numerator turn into? Or get really close to? Gets really close to 0. Okay. What about the denominator? Okay, gets really close to negative infinity. Gets larger and larger and larger in the negative direction. So let's think about this for just a second. I've got a 0 on the top. I've got an infinity on the bottom. This is not in indeterminate form. This has an answer. This has a finite limit. What is it? It's 0, okay? So the top is approaching 0, and the bottom's just getting bigger and bigger. So we're taking a tiny number and dividing it into a smaller and smaller piece. They're both helping it go to 0. Does that make sense? So that means that over on this end, it approaches 0. So even with just this information right here, we would guess that it does something like like this. Good ballpark. Okay, domain, intercept, symmetry, asymptotes. Okay, we've got a vertical asymptote. We don't have a, well, let's see, just a second. Do we have a horizontal asymptote here? Okay, at y equals 0. Y equals 0 is a horizontal asymptote out on this end right here. Okay, not on the right end. We don't have a horizontal asymptote on the right end. Okay, we've got some growth toward infinity. We've got this increasing without bound. Any questions there? Okay, so let's talk about increasing or decreasing. We could probably take some guesses here, but it would be nice to know specifically where this changes from increase to decrease, and vice versa. So let's find the derivative. So f prime is going to be bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Correct? So I'm going to write this as e to the x, x minus 1 over x squared. Good there? Okay. Factor it out, because what do I need to know about the first derivative? I need to know where it equals 0, and I need to know where it does not exist. Now, where does it not exist? At x equals 0, where that point's not in the domain anyway, so we don't have to worry about that. Where does it equal 0? At x equals 1. Okay, so here's the start of our sign line here. Remember, these are values of x. So I'm going to put a 1 on here, and the reason that's on there is because the derivative equals 0 there. Okay, remember, it doesn't exist there. Let me make a little bit more space. So let's pick a negative number and let's plug it in here. Pick a negative number, plug it in here. E to the x is positive, x squared is positive, so this is 100% determined by this guy right here. So it's negative. Pick any number you want in between 0 and 1. That's still positive. The bottom's still positive. And if I plug in a number between 0 and 1, I'm plugging in a small positive number. If I subtract 1 from that, I get a negative. So this is negative. Any surprise there? Nope. Okay, plug in any number you want past there. Positive here, positive here, positive here. Plug in a number bigger than 1, you're going to get a positive for all 3 of those, so we end up with positive. So I've got a function that does this. It decreases. I'm going to put a question mark, but we know what happens there. It doesn't exist, right? We've got a vertical asymptote. It's a point of discontinuity. It decreases, levels off, and then increases. Okay? All right. I'm going to go ahead and change colors for this because I'm going to find the second derivative. So let's go ahead and find f double prime. And I'm not going to use this form right here. I'm going to use this one because I think that'll be a little bit easier. I'm going to erase the 1. So this is going to be the bottom times the derivative of the top. So that's going to be x first times the derivative of the second plus the second times the derivative of the first. And then the derivative of negative e to the x. That's just the bottom times the derivative of the top. You want to double check me? Minus the top, x, e to the x, minus e to the x, times the derivative of the bottom, which is 2x. All over the bottom squared, so that's going to be x to the 4th. Now, we want to be a little bit smart about this. Those two make a 0. Let's see, I can take out, can't I? Well, let's see, I can take out an x out of each one of these. Okay, so if I do that, I'm left with an x distributed through to there, so that's going to be an x squared to the e to the x. Okay. No, you can't take out an x squared. Good? Just an x. I'm left with 1x here, and when I distribute it through, I get an x squared to the x. Everybody okay with that? And then I took out the x, so I'm left with minus 2x e to the x, and then this would be plus 2 e to the x, all over x to the fourth. Good there? So let's simplify this. I can cancel this with that, and I can take out an e to the x, right? So I get e to the x, I get x squared, I get minus 2x plus 2 over x to the third. Good there? What would we want to know about the second derivative? Where it equals 0 and where it doesn't exist. The only place it doesn't exist is at 0, where we've got a point of discontinuity, so we don't need to worry about that. Okay. Let's think about this guy right here. Does that factor? No. And if you plugged it into the quadratic formula to find the zeros for this, we're going to have, underneath the radical, we're going to have a b squared, so that's going to be 4, minus 4 times a times c, and that's going to be a 1, whoops, thinking ahead here, 1 and a 2. What's going to be underneath the radical? A negative, so we're going to have imaginary solutions to this. So does the second derivative ever equal 0? It doesn't, okay? So this is either all concave up or all concave down. Does that make sense? Okay. Now, let's put these pieces of information together. I need to make this a little bit smaller so we can see what's going on here. I'm going to draw the graph right here. Or draw it right here. I've got a vertical asymptote right here. Okay, it would be nice to have a point to graph. Do we have any points to graph yet? Well, there's one point we definitely want to find. It would have an x-coordinate of 1, because we know it goes down here, levels off for a second. So let's figure out, what do you get if you plug in a 1? You get e over 1. Okay, so this point right here is 1, comma e. And the graph does this. It comes down, hits this point. Whoops, let me make that look a little better. Comes down, hits this point, levels off, and then it goes up like this. Okay, now I'm going to make that fat so it looks like it actually touched it. And this, if it comes down and goes up, that suggests we've got some concavity. But we know it can't change. We know it can't, come down here and kind of do something weird like that. Okay, doesn't work that way. It's all concave up over here. And then over on this other side, we know we have a horizontal asymptote of y equals 0. So it runs along here, and we know it goes down, so it's got to be all concave down. So we've got this nice smooth shape like this. If we wanted to be really convincing about this, maybe we'd figure out what the value is at -1. And if you plug in a -1, correct me if I'm wrong, but don't you get -1 over e? Okay. Throw that in your calculator. It should look exactly like that. It should have a vertical asymptote here, a horizontal asymptote on the left side. It should have a min right here, and it should go through the point -1, and it'll be comma like -0.4 or something like that, maybe. Any questions?
So
yeah.
When finding so for finding point inflection 0 when it equals 0 does not exist, and therefore if it.
But remember, it's got to be continuous at that point. Okay. So because it's discontinuous at 0, we can't have a point of inflection there.
Yeah.
Okay.
So therefore, whenever a graph, part of a graph is concave up at rest.
The whole part of it has to be concave up.
This,
We could also plug in numbers into this, and what you'd find is if you plug in a positive number, every one of these is going to be positive. And if you plug in a negative number, you're going to have a positive here, and a negative there. Okay. So you'd end up, if you plugged in a negative number, you'd have negative concavity at that point. So you know the whole thing's got to be concave down. Does that make sense? Okay. There is a lot of logic that goes into these. Okay. You got to really put the pieces together. Okay. I've got 20 minutes left. I'm not going to be able to finish both of these completely, but we're going to at least get some rough sketches and get the ideas outlined. So let's take a look at this one right here. The first thing we notice is this has got trig functions in it. So if trig wasn't your favorite, this might present a bit of a challenge. But trig functions are also periodic. We haven't run into one of these before, but the period on this one is going to be 2 pi. Whatever shape we make, if I can graph it from 0 to 2 pi, I can just repeat that same pattern every 2 pi units after that. Okay? So again, let's talk about domain. This wouldn't exist when the denominator is 0, and that would happen when sine is equal to 1. So think about what sine looks like at pi halves. Okay? So x cannot equal pi halves. That's not in the domain. And remember, this is periodic, it repeats, so we could put 2k pi. So every pi halves and every 2 pi units after that, it's going to have a vertical asymptote probably. Because we're dividing by 0, and that's usually what happens, right? Okay, we'll check that. Okay? Let's check intercepts. If I plug in a 0, I get a 1 on the top. I get a 1 minus 0 on the bottom, so I get a 1. It goes through the point 0, comma 1. Okay? We also, so that's the y-intercept. I want to know what the x-intercept is. Okay? So I'm going to plug in a 0. I'm going to set the whole thing equal to 0. So when does the numerator equal 0? Let's think about what cosine looks like. Cosine looks like this. Hits 0 here and hits 0 here. What's this one? Pi halves. But pi halves isn't in the domain. Okay? So pi halves isn't in the domain, but this one right here is x equals 3 pi halves. So the only x-intercept that we've got on the interval from 0 to 2 pi is going to be 3 pi halves. And every 2 pi units after that. Does that work? Okay. You guess there's any symmetry here? Let's plug in a negative x. Cosine of negative x, because it's an even function, is the same as plugging in a positive x. Sine is an odd function, so if I plug in a negative x, I can slide that negative out front, and here's what I end up with. Is it the exact same? No, so it's not even. Is it the exact opposite? It is not, okay? So no symmetry. So we're going to graph a cycle from 0 to 2 pi, and then we just have to rely on the fact that it repeats. Okay. Next up are asymptotes. So let's think about those for a second. And maybe I'll do this. Maybe I'll do it up here. Okay. So the asymptotes are going to be end behavior and vertical asymptotes. End behavior, this does the same thing over and over again. So it's not like we're going to have a horizontal asymptote or something like that, or it's going to just continue to increase and increase and increase because it repeats the same shape over and over and over again. Okay? So we don't need to check what's happening at positive infinity or negative infinity, okay, because it's just repeating the pattern. But I do need to check this. I do need to check the behavior around pi halves. And I want to approach pi halves from the positive side and the negative side. So let's see what we end up with here. So this is the cosine of x, and this is 1 minus sine of x. Okay, now cosine looks like this. And 1 minus sine looks like this. It's been moved up 1 and been flipped upside down, so it actually looks like this. That's what 1 minus sine looks like. And we're interested in right here. So as we approach pi halves from the positive side, from the right side, these are approaching 0, but they're negative. These are approaching 0, but they're positive. Now, that's one way to do it, but I still get 0 over 0. So what's the answer? Use L'Hopital's rule, okay? I could just do it by substitution. If I plug it in, I get a 0 on the top. I get a 1 minus 1 on the bottom. So I end up with 0 over 0. So let's apply L'Hopital's rule. So if I apply L'Hopital's rule, I've got the limit as x approaches pi halves from the positive side. Derivative of the top, negative sine of x. Derivative of the bottom, negative cosine x. Well, that's just tangent, right? So what does tangent do? Let's see. Yep, did we get that right? Yeah, I think we're fine there. We get negative here, negative. So does that? Goes toward positive infinity, right? Oh, from the positive side, yep. So we're approaching it, whoops, over here. That, make that look right. There we go. So we're on this side, so it's heading toward negative infinity, right? And I could go through the trouble to set this up again and approach it from the negative side. But isn't the same thing going to happen? Aren't I going to get 0 over 0? Yeah. So I'm going to differentiate using L'Hopital's rule. So I'm going to check the behavior here. So I'm looking at this side. So it's going to approach positive infinity. So at pi halves, it's going to look something like that. It's going to go up here, and it's going to go down here. Good there? Okay. So there are the asymptotes. Now let's figure out intervals at least of increase and decrease. So I want to find the first derivative. So I've got the bottom, 1 minus the sine of x, times the derivative of the top, negative sine of x, minus the top, cosine of x, times the derivative of the bottom, and the derivative of the bottom, negative cosine x. All over the bottom squared. So this is going to be 1 minus sine of x, quantity squared. So let's take a look here. I've got, if I distribute through, I've got minus sine of x, I've got plus sine squared x, and I've got plus cosine squared x. So what do I end up with here? I end up with 1 minus sine of x on the top and 1 minus sine of x quantity squared, quantity squared on the bottom. So I end up with a 1 on the top and a 1 minus sine of x on the bottom. What do I want to know about this? Where it equals 0 or where it does not exist, right? Will it ever equal 0? Nope. Okay, where does it not exist? At pi halves, okay? Where we've got our point of discontinuity already, where we've got our vertical asymptote, okay? Any questions there? Okay, so we've probably got a pretty good idea of what's going on here, okay? This is, so if we do a little sine line here, the only important point here, let's go from 0, let's start at 0 and let's go to 2 pi, because we know that's one cycle. The only point that's important as far as the first derivative goes is pi halves. So if I plug in a value in between 0 and pi halves, we just want to know whether it's positive or negative, because that will tell us whether it's increasing or decreasing. Based on what we have right here, what do you think it's going to be? It's going to be positive, but let's just double check. So plug in pi fourths. You'd have a positive on the top and then we'd have, on the bottom, we'd have 1 minus something that's got to be less than 1. So we end up with a positive down here. So we end up with positive first derivative here. Okay, we know we've got and I'll write it here, we know we've got a vertical asymptote there. And then everywhere on this interval right here, it's got to have the same either increase or decrease. What would we guess it is? Okay. Not here. Okay. Okay. So if we plug in a number that's, say we plug in pi, I get positive here. Sine of pi is 0, so I have positive on the bottom. So what do we know about this function? Always increasing. Always increasing. Okay? Okay. So let's see. Let me come back here and let's talk about what we've got here. I've got a couple of points that we want to put on here. Those two. And we've got the vertical asymptote. So from this point right here, 0, 1, it always increases, right? Goes like that. It goes through, let's see, let's say that's pi, and that's 3 pi halves. Okay, and let's say the end of the paper right here, there's our, whoops, there's, whoops, erase that, did not mean to do that. Goes through there. So we know that it headed toward negative infinity here, so it's going to start down here, go through this, and what would happen if I plugged in the end point right here, 2 pi? What do we get if we plug in 2 pi into this? We get a 1 on the top, we get a 1 on the bottom, so we get 1. So it comes here and it ends right there where it left off. So this kind of looks like we're going to have a shape that does something like this. Just repeats like that. It looks a little bit like a tangent. It's not a tangent, but it kind of looks like one. Okay, any questions there? Okay.
After 2 pi, wouldn't you keep continuing until keep going up until you reach another
When we reach 5 pi halves.
Yeah.
Yep. Mm-hmm. Yeah. But it's going to be, so it's going to be this shape from here to over to here, just repeated over and over again. So we could take this piece over here and put it right there, and it would look exactly the same. Sure. Mm-hmm. Let's check that. So we want to check concavity on this one, and remember, since the first derivative got simplified to this actually isn't too terribly bad. Let's double check it. So I've got the bottom. What's the derivative of the top? 0 minus the top times the derivative of the bottom. Negative cosine, right? All over the bottom squared. So I end up with, let's see, a 0 here. I end up with cosine of x and 1 minus sine of x quantity squared. Okay, when does this not exist? Pi halves. Okay. When does this equal 0? Yep. When cosine is equal to 0, and that cosine, we already talked about this, that would equal 0 at pi halves and 3 pi halves. Pi halves isn't in the domain, so 3 pi halves is a point of inflection. So we're concave down here, and then concave up after that. So each one of these branches kind of looks like this. And this point right here would be 3 pi halves, comma 0. Okay, any questions there?
So when finding points, the points
Like,
you want to look for are intercepts,
definitely,
and
maxes and mins, and points of inflection. Mm-hmm.
Okay.
And it turns out on this one, we found the y-intercept, so we found this point right here, 0, comma 1.
Mm-hmm.
We found the x-intercept was 3 pi halves, comma 0. And that happens to also be a point of inflection. Any maxes or mins? Nope, because it never changes from increasing to decreasing, or vice versa. Okay. Any questions?
So points would be inflection, axiomin, and
Intercepts.
and then the rest you can figure out.
If you need to pick additional points to get a better sense of what it looks like, then you pick additional points. Yep. So intercepts, maxes and mins, points of inflection. You definitely want to have those. Okay. Any questions? Okay, let's flip the page over. This one's pretty wild. This is problem number 24. I think what I'll do is I'll try and record a video that explains more in depth how to do this one. But let's at least go ahead and get started with this. Let's talk about the domain for just a second, because on this problem, the domain is very interesting. You can plug anything you want into this guy right here, but you can't take the square root of a negative number. So what we want to know is, when is x squared plus x, when is that greater than 0? Greater than or equal to 0, I suppose. Between -1 and 1. Anybody know why? Can you explain why? Okay, so we could go through that argument, or we could look at a picture. Juan's exactly right, but let's look at a picture. What shape is this graph? Parabola, opens up, has an x-intercept at 0 and an x-intercept at -1, so it looks something like this. That stuff underneath the denominator, or excuse me, underneath the radical is a parabola, and it looks like this. The only part of this parabola that we wouldn't be able to take the square root of is where it's below the x-axis. And where is it below the x-axis? Between -1 and 0. Okay? So the domain on this problem is from -infinity all the way to 0, including 0, or sorry, to -1, and then starting up at 0 and going to positive infinity. Okay? That's where this graph is going to exist. So we definitely want to check what's going on at those endpoints. Okay? Do we actually have values? Do we have values? Can you plug in a 0? Yeah, if you plug in a 0, let's go ahead and do the intercepts right now. If you plug in a 0, you get 0. Does this ever equal 0? Well, clearly it does. There's at least one place where it does. Let's find out other places where it does. In order to solve this, here's what you'd do. You'd move this to the other side. Move the -x to the other side. Remember all this 1050 stuff? This is actually from 1010. Square both sides. So that's going to give me x squared plus x equals x squared. There's an x on both sides, or an x squared on both sides. So this would be 0. So the only x-intercept is 0, which happens to be the y-intercept. So this only hits the x or y-axis in one place. It only hits at the origin. Okay? So it might be interesting to figure out, well, what happens right here? What happens at -1? Can you plug in a -1 into this? And if so, what do you get? Plug in a -1. You get -1 squared. That's 1. Minus 1. That would be 0. Square root of 0 is 0. Minus a -1. Positive 1. So right now, this is what we've got. We know it goes through this point and that point, and there are no points in between there. So our job is to figure out what it looks like over here and what it looks like over here. Okay? And somebody have their assignment really quick. Is this on your assignment? I think it is. 24? Okay. So here's what I'd like you to do. Between now and, say, the end of the day, I'm going to record a video that explains how to do the rest of this problem. And you don't need to get too carried away. On the test, I'm going to give you something that's kind of middle of the road. These last couple of problems, those are quite difficult. Okay? Lots and lots of information there. Okay? Lots of pre-calculus stuff that you're like, oh, I don't remember doing that for a long time. Okay? You know, A lot of times you can tell the concavity just by looking at it. Okay, if you need to find the second derivative, they've been fairly kind on most of these, because most of the time the second derivative, you'll be able to look at it and tell, oh, that's always positive, or that's always negative, or it's either got to be one or the other, okay, on certain intervals. Usually not going to be a point of inflection, okay, at least on these really ugly ones, okay? All right, so I'll record a video that shows how to do that, but that's it for 4.5, so you can consider that official, all right? Thanks.